So today we're going to talk about fossil fuels. We're going to go through a couple concepts, starting off with the most important plot ever, according to the author of our textbook. And then we'll look at an overview of coal, oil, and gas. Looking a little bit at the chemical energy, how do these things give us energy? And then we'll look at some of the pros and cons of fossil fuels and the future of fossil fuels, which again, this will be something that we'll be talking about all through the quarter. So here is the most important plot ever, according to our author. So this plot here is, on this side, it's energy. So energy used by human beings, and then on the x-axis is the year. And so the author makes the point that throughout all recorded history, up until very recently, right, energy output was pretty much on the count of muscle and firewood. And then with the discovery of fossil fuels, not that too far back in our history, we've had just an enormous explosion in energy scale. And so you get this interesting plot. And of course, the point is probably the point of this discussion, this chapter, is that these fossil fuels are finite. We don't exactly know how much there are, but they will more than likely eventually run out. And then sort of what happens after that is a big question mark. And so the point brought up is that we live in an abnormal time, right? If you look at throughout history, this is a very unusual time if you look at just energy scale, which of course has had a huge impact on our civilization. At this point, fossil fuels still account for about 80% of our total energy use. And of course, the big question is, what will the future hold? So we're going to sort of talk about three major kinds of fossil fuels: coal, oil, which is also we call petroleum, and natural gas. Now these are essentially a form of ancient solar energy that plants once captured and stored as chemical energy underground. And you can think about it as this amazing resource that we've discovered and are now using. And while they were sporadically used previously, their use really began to skyrocket around the time of 1850. And so here's a plot kind of showing this here. And again, this is on the y-axis, this is terawatts, so energy use, and on the x-axis, the year. And you can see here that there wasn't much in the way of use until that 1850, and this plot breaks it down into sort of coal, oil started to being used around this time here, and then natural gas a little bit later. And of course, again, this is sort of this, the sort of a blow up of that plot we were just looking at. As far as, before this, the energy output was relatively small comparatively. Okay, so chemical energy, again, this is what's stored in fossil fuels. And so chemical energy is released when fossil fuels are ignited in the presence of oxygen. We're not going to spend too much time on the chemistry here, just to sort of see what's going on here. So with coal, we can think of that as being carbon. Gas, we're going to look here at methane, and then oil, this chemical agent here is octane. And so these are basically what we find underground. And when ignited in the presence of oxygen, so that's key, so here. And so basically what's going on here is on this side are the things that we're adding together. This would be the fossil fuel and oxygen. And on the other side is what comes out after this reaction. And so you can see that number one, carbon dioxide, in some cases some water, and then a large amount of energy. A couple things to note here is first of all, if you look on either side of the equation, you're going to have what you can consider conservation of mass. And so, for instance, if we look at the natural gas, and so at the starting out point, we've got one carbon. So these are chemical elements. Again, we're not going to focus too much on this, but it's probably good just to be aware. And then H4 means there's 4 hydrogens. So 1, 2, 3, 4. And then we're going to add 2 oxygen molecules, O2, which is a total of 1, 2, 3, 4 oxygen molecules. And so that's sort of the initial case. And then afterwards, we have CO2 and then 2 water molecules. which would be, again, 2 H's, and since there's 2 of them, 4 H's, and then an O and an O. And then just to make this even clearer, I'll go ahead and just erase this. And so carbon dioxide is C and 2 O's. And so you can see that there's, if you just cross them out, so 1, 2, 3, 4 O's, 1, 2, 3, 4 oxygens, 1 carbon, and then 4 hydrogens. So again, it's basically rearranging these atoms into different molecules, and this releases this chemical energy. And so in this chart here, we get a feel, again, for one of our things that we like to look at is basically how energy rich are these particular things, and we find out that these fossil fuels are pretty much the pinnacle of energy release as far as kilocalories per gram. And again, so here's this sort of chart showing this. So again, gasoline at 11 kilocalories per gram. If you remember, we sort of went through and looked at food products, and so the fat in our food gives us about 9 kilocalories per gram. Carbohydrates 4, but again, not as high as gasoline. And then you can look through this list of things that we would think of as being very energy rich, but indeed pale in comparison when compared to fossil fuels. So some of the pros, well, first of all, a very high energy density. Again, pretty much the pinnacle that we have of kilocalories per gram. There's some exceptions, and we'll talk about them, but as far as most common things, this is a really great energy density. Safety, they're generally not explosive. So you see in the list TNT, right? So these things are flammable, right? They're not super safe, but they're not the kind of things that are going to have massive explosions. And cheap, all right? And so here's where the rubber really hits the road. And so, suppose, to get some comparison, we hire someone to do some work, like dig a hole or something, whatever it might be. And so if we look at the human being output of about 100 watts of power, all right? And so let's say that we have this human being working for, $15 an hour for 40 hours. So when you multiply that together, you get $600. Now 100 watts, and so this is where it actually is kind of easy. If we look at sort of the energy that this person would be providing, we'd take 100 watts, and again we're looking at like a 40-hour work week. And so when we do this now, 100 watts, what we'd want to do there is we'd want to convert that over to kilowatts. And so how would I do that? I'd take this and write it as 0.1 kilowatts, right? And so I'm taking that 100 watts, and again, a kilowatt is 1,000, and so this is 0.1 kilowatts. And so 0.1 kilowatts times 40 hours gives us 4 kilowatt hours. So again, that most important plot ever. Before fossil fuels, you're talking about muscle and firewood. So here's, how much does muscle cost, right? So to get this person to work 40 hours, whatever they're doing, 4 kilowatt hours is the energy you get, the result. And again, that costs $600. Well, to get the same output from, say, a coal-powered power plant, and this is, again, getting our electricity, you're talking about something like 60 cents. So this is definitely much cheaper than other, these, at the time, other sources of energy. Perfect storage. This is really, fossil fuels are a great form of long-term storage, again, of ancient sunlight. Food production, we won't, if you look at this idea of the Green Revolution, and so this is a period around 1950 when fossil fuels, both as an energy source and also, importantly, as a fertilizer, led to the modernization and mechanization of agricultural practices, basically just making agriculture into a much bigger and make it much easier for food production, which has led to, again, a lot of positive things. A lot of people being able to eat. And then finally, a technology catalyst. You can argue that fossil fuel production has led to this technological revolution that we now live in. That chart of muscle and firewood, and then all of a sudden the fossil fuels, well, that also happens to align with this just a massive increase in healthcare advances, scientific knowledge, and overall better living standards for everybody. Cons, well, the big cons, and we're going to talk much more about this in later sections, is climate change. And so where does this, well, the big thing here is large amounts of carbon dioxide emission. And this, again, we'll talk about this in upcoming sections, but large amounts of CO2 emission change the equilibrium temperature of the Earth. And this is this idea of climate change. So we'll talk again about what this does and sort of the effects that this has. There's also just an environmental toll in extracting these fossil fuels most times. So this can be destructive to the environment. So these are sort of the main cons that we're going to deal with. And so what is the future going to hold? And I guess that's what we're going to, sort of spend some time sort of looking at and trying to figure out a little bit better, but then this big question mark here. And so here's the author goes through and just kind of goes through a couple different things that could happen, because again, this is an open question, right? But so for like number one, we discover some new form of cheap energy that's not yet known or appreciated. That's a game changer, and then we quickly abandon fossil fuels. Known renewable energy sources like solar or wind are developed to the point of being effectively superior to fossil fuels, so that the market naturally moves us to those and away from fossil fuels. Now, there's also the possibilities of climate change concerns resulting in politically enforced financial disincentives to using fossil fuels, and people talk about a carbon tax, and so that we also migrate away from these. And then perhaps increased difficulty in extracting fossil fuels drives their price up, so that again the market ultimately is forced to accept less convenient and more expensive forms of energy. A fifth option, we fail to find suitable substitutes to this precious and unique resource, so that the global geopolitics increasingly center on competition for remaining fuel, likely touching off destructive resource wars. So not sort of a pleasant outcome there. And then six, perhaps together with the previous point, society slowly grinds to a less energy-rich state, diminishing agricultural capacity. Again, as we talked about, these have helped the food production, and decreasing both the number and standard of living for people on the planet. And so again, these are some options, and again, we're going to spend a lot of time in the next parts of the course kind of discussing these. All right, so what time scales are we talking about? And this is really one of the big questions. And so we go through in the text and sort of discuss some options and some sort of science on this. So the sort of fundamental sort of best guess that we would have right now is this RP ratio, the reserve to production ratio, and this is just literally a means, to assess the time remaining. This should be remaining for a resource of quantity. This should be of R units being used over produced P. And so it's basically R is how much of this resource we have remaining. And so here's the R category, and then P is how much are we using per year. And so, like for instance, right here. So for the world oil, right now, some estimates give us at 1,700 giga barrels. And so this BBL is a barrel of oil. That's what that unit means. And so again, by some estimates, 1,700 giga barrels of oil are left. And then if you look at what we're using, 30 giga barrels of oil. And so this RP is literally just taking the R, 1,700 gigabarrels, and dividing that by 30 gigabarrels. So this is how much we have left, and this is gigabarrels per year is how you could think about those units. And so when we cancel that out, the gigabarrels cancel. Since the year is downstairs here, then this gives us this number here. When I figured this out, was about 60 years. And again, these are really uncertain. But if you look at sort of the numbers right now, this is sort of the rough estimate that we can get. Now, a couple things about that. There's a lot of things can change or just are unknown. And so there's a couple things the author points out. The production, the consumption rate is not steady, but on the whole has grown over time. And so, continued growth would actually shorten this time scale, right? So that's one thing that could change. New exploration and discovery adds to the reserves, lengthening the time scale, right? So that's something that would be, again, would prolong the lifetime of this. Advances in oil extraction technologies increase the amount of accessible oil, again, lengthening the time scale. Geological challenges limit the rate of production, lengthening the time scale, but also limiting resource availability. And then demand could plummet if superior substitutes are found. So again, it's really hard to say, but again, it's something that people look at because it is an important concept. How much longer do we have, right, until that question mark comes up in that plot. And so here's a plot. This is U.S. oil production. Again, so this is mega barrels per day and by year, and they put sort of different things in here, for instance, fracking. So this is a new way of finding oil that's only been developed recently, that has freed oil that was before more difficult to get to, and of course that led to an increase in oil production, and again, found a bunch of oil that people didn't realize we were going to be able to use. So again, this stuff was really in flux, but again, something that it's probably good for us to start thinking about. So summary, our current world would not be possible without fossil fuels. However, they also bring a number of downsides, which we're going to talk about much more as we go through the course. And then no one can be sure of the timetable, but the fossil fuel supply is something that is finite, and so it's definitely something that's good to talk about. What are we going to do next?